Hello everyone, welcome back to my channel Study With Me. Today I'm going to explain about another example of paper 2 higher level prediction questions. Again, it is not 100% guaranteed that this question will be appear in the exam. Rather, you can think this as a mock exam to check whether you are ready for the exam or to investigate what kind of topic that you're still struggling with, so you can go back and then do the revision on that particular topic. If you find this video is helpful, please don't forget to subscribe and let your other friend knows about my channel to support me. And now let's get started. Sodium dithionite is a reactive water-soluble salt with the molecular formula Na2S2O4. A 15-gram sample of sodium dithionite is dissolved in water. When the solution is boiled, the sodium dithionite reacts to form other sodium salt. The equation for this reaction is shown. Calculate the mass of water consumed in this reaction using section 6 of the data booklet. So we've got the mass of sodium dithionite, which is this one. So we can calculate mole, which is 15 divided by its molecular mass, which is 174.12. That would be 0.861 mole. So to find the mass of water, we can do the mole ratio. So the coefficient is 1, so mole of H2O would be half of this mole of sodium dithionite, which is 0.0431. So now we can calculate mass of water, which is the 0.0431 times 18.02, and you get 0.776 gram of water. Sodium dithionite reacts with water to produce the bisulfide ion HSO3-. In the following Lewis structure A, the S atom of the bisulfide ion is represented with an expanded octet of electrons. Draw an alternative Lewis structure B in which the S atom has an octet of valence electron. Okay, so a structure of this shows the S atom forming 1, 2, 3, 4, 5, 6 bonds, giving it an expanded octet of 12 valence electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For the S atom to have an octet electrons, the pi bonding pairs of the S double bond O must be placed on the O atoms, forming additional lone pairs. Okay, thus the structure B would be S, O, 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 and O here. Sorry, this would be H. So this would be 2 plus. This minus, and this minus. Okay, so for the structure B, the oxygen atoms all have -1 charge. So the S atom must have a charge of +2 to give the molecule a net -1 charge. So now it has 1, 2, 3, 4, 5, 6, 7, 8. So it has an octet of valence electron. Explain why one of the structures is preferred based on the formal charges of the S and O atom. So if we compare for both structure, now let's compare structure A. So formal charge of X would be valence electron, which is X, minus half times how many bonding electron, so it is 12. There is no non-bonding electron, so that would be 0. But for structure B, formal charge of S, that would be 6 minus bonding electron would be 8, right? And there is no non-bonding electron, so that would be +2. Okay, so formal charge for structure A is all 0, so that's why the structure A is preferred compared to the structure B, because the formal charge for structure A, it's all 0. So the structure A is preferred as the formal charge of S, it's 0 compared to structure B, which S has a formal charge of +2. Sodium dithionite ion reacts with aqueous sodium hydroxide to produce a mixture of sodium sulfite Na2S and sodium sulfate Na2SO3. The equation for this reaction is this one. State the values of X, Y, and Z. That would be 3 and then 6, and this one would be 5, and this one would be 1, and this will be 0. In a disproportionations reaction, one reactant is oxidized and reduced. Explain why the reaction of dithionite ion with sodium hydroxide is disproportionations reaction. Disproportionations reaction is a reaction which the same element is simultaneously oxidized and reduced. Let's copy it down. So Na2S2O4 plus 6 NaOH produce 5 Na2SO3 plus Na2S plus 3H2O. Okay, so this -2 plus 2 plus 1, -2 plus 2 plus 1 from 1 Na, -6 plus 2 because Na2, so plus 6, but for 1 Na is plus 1, this one plus 6, this one -1 plus 1, sorry, plus 1, plus 1, -2 Na, okay, and then this one -8 plus 2 plus 6, so this plus 1, and this one plus 3. As you can see, S here, plus 3 to plus 6 oxidation, and for S here, reduction, right, from plus 3 to plus 1. So Na2SO4, Na2SO3, oxidation state increases, which is plus 3 to plus 6, and Na2SO4 to Na2S oxidation state decreases, plus 3 to plus 1. Sorry, -2, not plus 1, this one. So to here, okay, -2. A student measures the reaction rate of sodium hydroxide with an excess of sodium dithionite. The following graphs show how the concentration of sodium hydroxide and NaOH changes over time. Using the information in the graph, calculate the initial reaction rate in mole per decimeter cube per minute. So to calculate the rate, that would be the change of concentration. You can pick any point and time. So that would be 0.05. Okay, I picked this one. 0.05 minus 0.036 divided by 66 minus 0 time. Okay, so that would be 0.000212, or 2.1 times 10 to the power negative 4 mole per decimeter cube minute per decimeter 1 minute to the power negative 1. State the order of reaction with respect to sodium hydroxide, giving a reason for your answer. NaOH would be to the power 0, as the concentration of NaOH has no effect because the gradient of the graph, this is the concentration, and then the time when the when you draw the line here. Okay, so this is a graph for 0 order of reaction, so that's why the concentration of NaOH has no effect because of the gradient of the graph. Iodine pentafluoride IF5 is a liquid. The IF bonds in IF5 are highly polar. Explain why I and F atoms form polar covalent bond. So I and F, between I and F, F is more electronegative compared to I, because actually fluorine is the most electronegative element in the periodic table. So this would be partially negative, this would be partially positive. So F, it's more electronegative, that attracts bonding electron density more strongly. Most of the bond angle in IF5 are equal to 90 degrees. State the molecular geometry of IF5. That would be square pyramidal. Because I has 6 electron domain, which has 1 lone pair right here. Draw the shape of the IF5 molecule, including any non-bonding electron pairs on the I atom. As I already draw it here, so I will draw it back. So F, F, F here, like this. Explain why some of the bond angle in IF5 are not equal to 90 degrees, because there is a lone pair exists which repels strongly electron pairs, so the bond angle is less than 90 degrees. When IF5 reacts with fluorine gas, gaseous iodine heptafluoride IF7 is formed. A 3D model of the IF7 molecule is shown. Explain why IF5 is a liquid at a room temperature, whereas IF7 is a gas. The bonds in IF, the bond in IF7 interacts through London dispersion force, as it is symmetrical, which weaker than dipole force in the molecule of IF5 due to asymmetric and polar IF7. So that would be 1, 2, 3, 4, 5, 6, 7. So that would be like this. So it's symmetrical and there is no lone pair, so the dipole moment is cancelled. But for IF5 we have lone pair, so it is a polar molecule, so it contains, or it has a dipole force, and but for this one is London dispersion force. So London dispersion force is a weaker intramolecular forces compared to dipole force. FeNO3 iron nitrate dissolves in water to produce a yellow solution. State the electron configuration of the Fe3 plus ion. For Fe only, that would be Ar and Ar4s2 3d6, okay, or for Fe26 2 3 plus, so you will take 3 electron from 4s2 and 1 from 3d6, so that would be Ar 3d5. When iron nitrate dissolves in water, a complex ion X is formed. This ion is a weak Bronsted-Lowry acid. Draw the structure of ion X using wedge dash notation to indicate its shape. Transition metal typically bond to a 6-water ligand. Okay, so now we can draw Fe that is attached to 6-water ligand. So that would be OH2, and this would be OH2, 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 this also OH2, and this OH2, and 3 plus. Okay, a 0.25 mole per decimeter cube solution of iron nitrate has a pH of 3.23. Calculate the Ka of ion X. So H plus, it's 10 to the power negative pH, which is 10 to the power negative 3.23, and it's 5.85 times 10 to the power negative 4. So H plus, to calculate H plus, the formula is Ka times M, right? So because of the square root, so let's remove the square root. So squared, so that would be Ka times M. So Ka would be H plus squared divided by M. So 5.85 times 10 to the power negative 4 squared divided by the concentration, which is 0.25, and you get 1.39 times 10 to the power negative 6. Explain why the solution of ion X is yellow using section 17 of the data booklet. Section 17. Okay, so it's yellow. So the it absorbs violet light, as this is complementary to yellow. So the answer will be the solution absorbs violet light, as this is complementary to yellow and there are 3 orbitals in the lower level and 2 orbitals in the upper level. The absorbed light excites electron from the lower energy to the higher energy. So as you can see here, Fe, it's 3d5, Fe 3 plus. So the d orbital 1 2 3 4 5, so that would be 1 2 3 here, and then the higher energy d orbital, that would be 2 electrons. The aqueous Fe3 plus ions are reduced in the following voltaic cell: Fe and Pb. Okay, Fe is more reactive than Fe, it's more reactive than Pb. Therefore, Pb would be reduction. This would be oxidation. So if it's oxidation, that would be in anode, and this one would be cathode. Oxidation always takes place at the anode, and reduction always takes place at the cathode. Calculate delta G for this reaction using section 1, 2, and 24 of the data booklet. To calculate delta G, we need NFE, so we need electrode potential, cell potential. So this E cell would be reduction minus oxidation. So let's go to the section 24. So we've got Pb and Fe. So for Pb will be for 2 plus, Fe 3 plus 2, 2 plus. So Pb will be negative 0.13, and Fe would be plus 0.77. So that would be 0.77 minus 0.13 would be 0.90 volt. So here would be N negative 2 times Faraday, which is 96,500 times 0.9, that would be negative 733.7 kilojoule per mole. Based on your answer to part C1 and section 24 of the data booklet, explain why the Fe3 plus ions are reduced to Fe2 plus ions but not to solid iron. So why Fe3 plus aqueous to Fe2 plus aqueous instead of Fe solid? The answer, because delta G, it's negative, which is spontaneous. Okay, E for Fe2 plus aqueous and FeS half cell, it's negative 0.45 volt. And for Pb2 plus aqueous and PbS half cell is negative. Okay, this one should be negative 0.45 volt. And for Pb2 plus Pb solid is negative 0.13 volt. So Fe2 plus to Fe solid, it is less positive than Pb2 plus and Pb, right? So in this case, the E cell will be less positive. So delta G will be positive. So it's not spontaneous. All right. So to make delta G negative, E cell must be positive, as it is negative and Fe. So if we do Fe3 plus to Fe2 plus, which is, okay, so this is not the answer, so I'm just explaining. If a Fe3 plus becomes Fe2 plus, aqueous, and then aqueous, okay, so the half cell is 0.77 volt, right, which is more positive than Pb2 plus and Pb. So because it is more positive, so it will produce, or it will make the delta G negative. But if it's less positive, like Fe2 plus and Fe solid, it will not be able to reduce. Okay, so that's why it is used Fe3 plus to Fe2 plus, because it is more positive, so it will produce positive E cell, so will produce the spontaneous reaction, rather than using Fe2 plus become Fe solid, which is less positive, so it will not be able to reduce the Pb, and the delta G will be positive. When benzene is added to a mixture of compounds A and B, a reaction takes place. The structural formula of the two acids are shown. State the names of compound A and B. Compound A is nitric acid. Compound B, sulfuric acid. In the first step of the reaction, compound A acts as a Bronsted-Lowry base and compound B as a Bronsted-Lowry acid. Draw the structural formula of the conjugate base in this reaction. So the reaction would be H2SO4 plus HNO3, because H2SO4 is more strong compared to nitric acid. So H2SO4 will donate its proton, acting as an acid, produce HSO4 minus as the conjugate base, and H2NO3 plus as the conjugate acid, the one that received proton from H2SO4. So the conjugate base of this reaction is HSO4 minus, which is SO double bond O OH. Explain why the lengths of the S double bond O bonds in compound B change during this reaction. The pi bond of the conjugate base HSO4 minus are delocalized between SO bond, that is one of them is lacking OH bond. So the SO bond in the conjugate base is longer. If we compare between HSO4 minus and H2SO4, okay, in H2SO4, this one, Let's compare between this structure and this structure. Each S double bond O in H2SO4, there are two, okay, consists of sigma and pi bond, right? One sigma and one pi bond. When hydrogen ion is removed, so one H is removed, now become HSO4 minus, the number of pi bonds remain the same, but 3 atoms lacks of OH bond. So now it becomes 3O that lacks of OH bond. So the 2 pi electrons are delocalized over these 3 bonds. So it's like S single bond O has 2 over 3 of pi bonding pair between single and double bond. So the single bond is longer, so partial S double bond O in HSO4 minus are longer compared to the one that in H2SO4. A reaction mixture initially contains 6 times 10 to the power negative 2 moles of benzene. At the end of the reaction, the solution has a total mass of 340 grams and a specific heat capacity of 1.53. The temperature increased during the reaction from 15 to 31.1. Calculate the enthalpy change of the reaction. So delta T would be 16.1. You don't need to convert it to be Kelvin, because if you convert this to be Kelvin, this one to be Kelvin, and then when you find the difference, you will find again 16.1. So when it is delta T, no need to convert to a Kelvin. Calculate the enthalpy change. So the enthalpy change, first we need heat, because the enthalpy change will be Q divided by mole. So Q or heat will be MC delta T. So M340 times 1.53, which is heat capacity, times 16.1, that would be 8,375 joule or 8.375 kilojoule. So delta H would be Q divided by N. This would be negative because increase in temperature. So 8.375 divided by 6 times 10 to the power negative 2, that would be negative 139.6 kilojoule per mole. The rate law of the reaction is K, benzene, and A. The rate determining step is the formation of a carbocation intermediate. Draw the mechanisms of the rate determining step. So the benzene that would be N plus double bond or double bond. Okay, so this will go right here, the arrow, and this arrow also will go right here. So that would be positively here and NO2. DNO2 plus is acting as an electrophile, right? Accepting electron from the pi bond or pi system in benzene, forming the bond between C and N by breaking the N double bond O pi bond. The curly arrow represent the transfer electron pair from benzene to N atom and from the N double bond O bond to the O atom. So the intermediate is positively charged, delocalized over the 5C electrons. This is the carbocation intermediate. The rate constant was measured at 2 different temperatures. So this 25 should be 298 Kelvin. This would be 318 Kelvin. Using the data in the table and section 1 of the data booklet, calculate the active fusion energy for the reaction EA in kilojoule per mole. Remember this formula, ln K1 where K2 equal to EA divided by R, 1 over T2 minus 1 over T1. So let's rewrite the equation. So EA would be R ln K1 K2 divided by 1 over T2 minus 1 over T1. So that would be 8.31 ln 1.58 times 10 to the power negative 4 divided by 6.22 times 10 to the power negative 4, okay, divided by 1 over 318 minus 1 over 298, and you get 54 kilojoule per mole. Explain why concentration A appears in the rate law for the reaction. The reaction is first order with respect to A, which is HNO3. One molecule of HNO3 reacts to form NO2 plus that reacts in the rate determining step, forming carbocation. Okay, if we go back here, right? So HNO3 is involved to produce NO2, which is in the rate determining step. So the order of the reaction for reactant indicates the number of molecules involved in the rate determining step. If the rate determining step is not the first step, a reactant may affect K because it reacts to form intermediate that is not involved in rate determining step, right? But nitric acid or HNO3 is not involved in RDS, but it reacts to produce DNO2 plus intermediate. Since a rate determining step involves the reaction of NO2 plus ion, of course the rate determining step will be always involved in the rate of reaction. So that's why the order of reaction of HNO3 is 1. Gases nitrogen pentoxide and 2O5 reversibly decompose into nitrogen trioxide and a nitrogen dioxide. Define the term radical. Radical means a molecule or atom with unpaired electron. The NO2 radical can catalyze the decomposition of ozone into elemental oxygen O2. Write a series of 2 equations to show how the nitrogen oxide radical acts as a catalyst for this process. So NO2 radical, when it reacts with ozone, it will produce NO radical and oxygen. And NO2 radical react with ozone produce NO2 radical and oxygen. So from here you can see that NO2 is regenerated. State why your answer to part B1 indicates that NO2 radical is a catalyst and not a reactant, because NO2 radical is regenerated. So that's why it is catalyst. So it's consumed and then it produced back again. A sample of N2O5 has an initial concentration of 1 molar at 243 Kelvin at equilibrium. The concentration of N2O5 is 0.142 mole per decimeter cube. Calculate the equilibrium constant for the reaction Kc and state its unit. Kc, before that let's calculate how many moles, that is produce, or for NO3 and NO2 radical. So N2O5 NO3 plus NO2 radical. So initial concentration of N2O5, it's 1 molar, and after the equilibrium it will be 0.142. So 0.858 are consumed, so this would be 0.858 are produced, and this one also 0.858 are produced. So now Kc NO2 NO3 divided by concentration of N2O5, which is 0.858 times 0.858 divided by 0.142, which is 5.18. The enthalpy change for the reaction delta HR is plus 104.7 kilojoule per mole, suggests how increasing the temperature of the N2O5 sample would affect the value of Kc, giving a reason for your answer. So N2O5 NO3 plus NO2, delta H R is plus 104.7. So this forward, because it's plus, would be endothermic, and reverse would be exothermic. So increasing the temperature favor or shift the reaction equilibrium to, when you increase the temperature, it will absorb the heat, right? So that would be endothermic, so it will shift to the right because it increase Kc and yield. Okay, because, let me add, because the reaction favored endothermic. Now, part of the Born-Haber cycle for lithium oxide, Li2O, is shown. So there is Li2OS, and when the atomization enthalpy of oxygen, the reaction would be, it is not necessary to write this, but I'm just writing the reaction so you guys can understand how to construct the Born-Haber cycle. So Li2O, when it is formed through the standard enthalpy or enthalpy of formation, that would be from their standard state. So Li S plus half O2 gas, because Li2, so 2 Li. So now is atomization enthalpy of oxygen. So the this is the atomization enthalpy of oxygen, so half oxygen. And now atomization enthalpy of lithium, so from solid to gas, so this would be 2 Li gas plus half O2 gas. And first ionization energy of lithium, so ionization of energy, removing the electron, so the reaction would be 2 Li plus gas plus half O2 gas plus 2 electron. Li only lose 1 electron, but because of 2 Li plus, so that's why it's 2 electron. And then continue to electron affinity of oxygen, so that would be 2 Li plus plus O minus, and then plus electron, right? And because oxygen lose 2 electrons, so we've got the second electron affinity of oxygen. So plus electron here as well, but because it's already written here, so I don't need to write plus electron here. And then this is the enthalpy of the direct route, and the indirect route will be like this. As you can see, for the standard enthalpy of formation will be negative. This one will be positive because the same direction. This one will be positive, this one will be positive as well, this one will be positive as well. So write the reaction equation corresponding to the standard enthalpy of formation of lithium oxide. That would be 2 Li solid plus half oxygen gas would be Li2O solid. Using the values in the Born-Haber cycle in section 8 and 11 of the data booklet, calculate the standard enthalpy of formation of lithium oxide. To calculate delta HF would be half of delta atomization of oxygen, because half of oxygen, right? And plus 2 atomization enthalpy of lithium, because 2 Li, okay, and then plus 2 first ionization of lithium as well, because 2 lithium, again the same width, 2 Li, that's why 2 atomization enthalpy of lithium, and plus electron affinity, the first electron affinity of oxygen, right? This one, and then this one, and plus electron affinity, second electron affinity of oxygen, minus lattice enthalpy of Li2O, because different direction, right? For direct route and indirect route. So for atomization of oxygen, you can refer to the data booklet, oxygen double bond O. So that would be 498. So half of 498 plus atomization of lithium is known here. So 2 times 159 plus ionization of lithium, you can go to the table, ionization energy of lithium, which is 520. So 2 times 520, and electron affinity of oxygen, and second electron affinity of oxygen is available here. So electron affinity of oxygen, negative 141 for the first electron affinity, and then plus 750 for the second electron affinity. So minus 141 plus 753 minus 2,817. Then you will get negative 598 kilojoule per mole. All the group 1 oxides have the same ionic lattice structure. The melting points of the group 1 oxide are shown in the graph. Explain why varying the metal ion in the oxide affects the melting point of the material. Going down a group, the ionic bonds become weaker as the ionic radius of number of shells increases. Thus, the distance between cations or metal and anions, oxide ions, increases, causing this weakening electro weakens electrostatic attraction. Okay, so CS2 or CS itself has the biggest atomic radius, and when it becomes ion, of course it will have the biggest ionic radius. So the attraction between the nucleus from CS will be weak to oxygen, so that's why it will be easier to break. So the melting point will be decreased because it will be easy to break the bond between TCM and oxygen compared to lithium and oxygen. Lithium oxide reacts with water to produce lithium hydroxide, a strong base. Compound X is a weak monoprotic acid. A 50 centimeter cube aqueous solution of X changes color as solid lithium oxide is added. The pH of the solution is monitored during the reaction and the following pH curve is obtained. The question here, at one of the label point A to D, the pKa of X is equal to the pH of the solution. Using section 22 of the data booklet, suggest the name of X and give a reason for your answer. So this would be pKa, half of equivalence point. So pKa equal to pH. And this one, D, is the equivalence point. This one is half of the equivalence point. So suggest a name of X and give a reason for your answer. So using section 22, section 22, that would be the indicator. So what indicator that should be suitable for this titration? So the pH is around 5 point something. So the one that is suitable is methyl red. So methyl red as pKa equal to pH by point B. Explain why X would not be a suitable indicator for the titration of lithium hydroxide against hydrochloric acid. The previous one, it's between weak acid, monoprotic weak acid with strong base, where the pH, where the equivalence point is at around 9 something. So when the monoprotic weak acid changed to hydrochloric acid, the equivalent point would be at pH equal to 7. So as hydrochloric acid is a strong acid with equivalence point at pH equal to 7, the indicator will not change the color, as typically the pKa, it's plus minus 1 pH, right? pH unit. So the color will change after, because when we use methyl red, the equivalence point is at 9 something, while for the this new titration between the lithium hydroxide and hydrochloric acid, pH at 7, so there will be no color change because it's not suitable anymore. Based on the information and the pH curve, calculate the initial molar concentration of X in mole decimeter cube. So NLi2O, it's 0.009 mole at equivalence point here, okay? So it's around 9. So NLiOH equal to X, which is 2N Li2O, so 0.018 mole. So X will be 0.018 divided by 0.05. 0.05, this is the volume. So you get 0.36 mole per decimeter cube. So the pH curve show that X completely react once 0.009 mole of Li2O have been added here. So the pH increases sharply because the reaction is Li2O plus H2O produce 2 LiOH. So X is monoprotic acid, and 1 mole of X reacts with 1 mole of Li2O. So the mole of X is twice the number of Li2O at the end point. So that's why 2 times 0.009 is 0.018. So N is C divided by V. That's why 0.018 divided by volume 0.05 produce 0.36 mole per decimeter cube. Compound A and B have the following structural formulas. State the names of the functional groups in the compound A and B. For the compound A, we've got alkene and hydroxyl, alkene and hydroxyl. And then for compound B, we've got ketone and then carboxylic acid. Carboxylic acid. The reaction of compound B with the reducing agent sodium borohydride, which is NaBH4, produce a chiral compound C. Draw one enantiomer of compound C, indicating the stereochemistry of the chiral center using wedge dash notation. So the compound B has both ketone and carboxylic acid. When we oxidize the secondary alcohol, it will produce ketone, right? So now the other way around. So when we reduce ketone, it will produce secondary alcohol. Okay, so what happened to the carboxylic acid here? The sodium borohydride is a weak reducing agent that cannot affect the carboxylic acid. So that's why the carboxylic acid in the structure remains unchanged. So let's now draw the one enantiomer of compound C, which has the chiral center. It is a C, a carbon atom that attached to 4 different group of atoms. Okay, so that would be C. So this would be H, and this one would be, so this one would be OH, and then this would be CH2 3COOH, and this one would be CH3. Erythrosynthesis of compound B from compound A is shown. So this is the compound with alkene, and through addition will produce compound D, and then will undergo oxidation. So write equation for the 2 steps of this synthetic route, including the full structural formula of compound D and the reagents used in each reaction. So the compound would be when it's through the addition with water, and then phosphoric acid as a catalyst. So it will produce the alcohol. Okay, so this would have alcohol, secondary alcohol, and then oxidation will use reagent KMnO4 and acidic condition. Okay, so why it is on the secondary alcohol? So we will answer this on the next question. Explain the selectivity of the first step in your answer. So alcohol is formed, okay, alcohol is formed as it reacts with water with carbocation. This secondary carbocation is more stable than the primary carbocation. Okay, so this is the answer. But why it is the primary, why it is secondary but not primary carbocation? So decarbocation here, so when it is through the intermediate, so this would be the +1. So this secondary carbocation, and it attached to this alkyl and then this alkyl, right? CH2 and then CH2. So for the primary carbocation, that would be right here, right? So it attached to one alkyl only. So that's why secondary carbocation is more stable, or it will produce 2 butanol, on the second, so it produce on the second carbon compared to the first carbon, because secondary carbocation is more stable compared to the primary carbocation. Compound E is a structural isomer of compound A. The infrared and HNMR spectrum of compound E are shown. So from this IR, we can see that there is a peak at 1700 to 1750. So this is C double bond O, carbonyl, and there is HNMR spectrum as well. So the question is, deduce the structural formula of compound E using section 26 and 27 of the data booklet. So first, there is IR Sinol at 1700 to 1750 centimeter to the power -1, shows C double bond O present. So Sinol, there is also Sinol at 1 ppm here. Okay, indicate CH3 group as it is triplet, so it means it is next to CH2, next to a CH2, and there is Sinol as well at 2.45, right? 2.45 ppm. So that would be CH2 group, which is quartet next to a CH3 group. Okay, if we see the integral spectrum, so the integral Sinol between 2.2 to 2.7, right? 2.2 to 2.7. So the integral Sinol between 2.2 to 2.7, it's a ketone group. We can see it here. So it's a ketone 2.2 to 2.7. So we know this is a ketone molecule. So since there are 6 atoms, so there are 6 here, 6 atoms. So one of them is C double bond O. So there are 6 atoms. One of them is C double bond O. And there are CH2, CH3 as well. And now we leave with CH3 and then CH3 and CH2. So let's see how to draw. So now we've got CH3 and then it should be 6. So that would be CH and then CH3. So C double bond O, CH2 and CH3. That's all for the explanation for another example of prediction question for paper 2 higher level. Again, these questions is not guaranteed to be appear at the or during the exam. Instead, you can treat these questions as a mock exam to check whether you are ready for the exam or not. And if you find this video is helpful, please don't forget to subscribe and let you other friends know about my channel. Thank you for watching, and bye.